Dobar dan, ja sam Vladan Vuletic i želim da vas odvedem u čudesan svet nauke. Nauka je moj dragi prijatelj. Ona me je dovela iz Evrope u Ameriku, u grad Boston, na MIT, Massachusetts institut za tehnologiju, gdje sam profesor fizike. Pođite sa mnom. Dobar dan, profesore. Dobro jutro, Vladane. Merenje vremena je jedno od najstarijih naučnih problema. Već stari Egipćani su morali da mere vreme za poljoprivredu. U prvo vreme se koristila astronomija, posmatralo se položaj meseca, sunca, zvezda i tako dalje. Kasnije, za bolja merenja vremena, ljudi su izmislili mehaničke oscilacije, a satove koji se klate ili pomeraju. Kasnije, u 20. veku, atomski satovi su preuzeli merenje vremena sa najvećom preciznošću do sada. Do ove godine merilo vremena je bio sat cezijum atoma, gde unutrašnja oscilacija u atomima se dešava 10 na 10 puta u sekundi, to znači 10 milijardi puta u sekundi. Najnoviji satovi koriste optičke oscilacije koje su mnogo, mnogo brže, 1000 biliona puta u sekundi. I to su najbolji satovi danas. Ti satovi su toliko precizni da bi napravili samo jednu grešku u 10 na 18 delova. Šta to znači? Kad bismo imali hipotetički jedan sat koji postoji od početka univerzuma, od početka velikog praska, Big Banga, taj sat bi do sada grešio samo za nekoliko sekundi, za nekoliko nevjerovatnih sekundi. Satovi su najbolji instrumenti koje je čovečanstvo ikad izmislilo. Današnji satovi su toliko precizni da jedan efekat koji je prvo bio potpuno teoretski, koga je Einstein smislio, naime da vreme teče drugačije u gravitacionim poljima. Einstein je tvrdio da ako ste u gravitacionom polju, vreme tamo teče sporije. Šta to znači? To znači u principu da vreme kod mojih nogu teče sporije nego vreme na visini moje glave. Neverovatno, ali istinito, i to je današnji satovi mogu da izmere. Ako uzmete najbolje optičke satove, koji su samo, uzmete 2 sata i podignete jedan od njih, samo za 10 santimetara, vi možete da vidite razliku u vremenu koje protiče. Šta to znači? To znači da vreme više nije apsolutno, nego zavisi od gravitacije. Za nekoliko godina, i to je nešto na čemu i mi radimo, satovi će biti tako dobri da će moći čak da primete ako se neka osoba kreće blizu njih preko gravitacije te osobe. Mi pravimo te atomske satove u laboratoriji, koristimo hladne atome koje hvatamo i koristimo lasere da merimo oscilacije u atomima. Kao što rekoh, te oscilacije su neverovatno brze. Ista su oscilacije kao što svetlost oscilira 10 na 15 puta u sekundi ili 1000 biliona puta u sekundi. Te satove pravimo hladnim atomima koje hvatamo unutar vakuma u pomoću laserskih snopova i onda merimo vreme. Projekt, to je moj najteži projekt do sada. Gradimo projekt već 5 godina i sada dobijamo ili očekujemo prve rezultate. Mi hoćemo isto koristimo kvantnu mehaniku i takozvana uvezana stanja da napravimo te satove još boljim nego što su do sada bili za jedan, možda 10 ili 100 puta bolji. I na tome radimo. Vidjet ćemo kako će projekt da se razvije u toku sledeće godine.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory. So they're very big, long words, but ultimately you can think of LIGO as a telescope. But mostly when telescopes, when we use them, what they're used for is collecting light from the distant universe, from stars, from galaxies, but light. LIGO is a telescope that's used for detecting gravitational waves. So instead of light waves that come from stars, what LIGO is trying to do is measure gravitational waves that also come from stars, but in some rather special and unique stars. So the gravitational waves are emitted due to an object's gravity or mass. So you can just think of anything that's heavy, that has mass in the universe and moves around, is going to emit gravitational waves. So why is that so special? It's very special because we know that in the universe there are objects that have a lot of mass and therefore gravity, but they don't emit light. Now, if we want to learn about those objects and we want to understand what they are, we have to find some other messenger, because light is not bringing us that information. A very good example of that is black holes, right? Black holes are called black holes because they're black. They don't give off light, but they have a lot of gravity and they give off gravitational waves. Now you might ask, well, why should we bother to study black holes? So first of all, I mean, they're amazing and wonderful. Who doesn't love a black hole, right? I mean, you throw something at the black hole and it gobbles it up. But even more fundamental than that, we know that black holes are the building blocks of our universe. Without black holes, we couldn't put the universe together that we live in. So we should know something about them. So if you want to know something about black holes and they don't give off light, you have to use the messenger that they do send their information with, and that's gravitational waves. So LIGO was conceived as an instrument, like a telescope, to detect these gravitational waves from the collisions of black holes, and to do that, because we've all heard at some point or the other that gravity is a very weak force. We don't really agree with that in our everyday life, because when we jump up, my goodness, we get pulled right back down. We can't jump very high because of gravity. But then you can ask the question of, well, why don't we just, when we jump up and we fall back down to the earth, why don't we just fall all the way down to the center of the earth, which is the point where gravity is focused? The reason we don't do that is because all the other forces, in particular electromagnetic forces, are stopping us on the ground. So that's really why, so gravity is very weak, and so gravitational waves are very weak. And that's why Einstein thought they would never be useful. So now comes what's the achievement of LIGO. The achievement of LIGO is that to measure these very faint gravitational waves, you take mirrors that are 4 kilometers apart and you make them so still. So you have to protect them from all the forces on the earth that make them move, so that they only move when the gravitational wave comes by. And that motion is about 1,000th the size of a single proton. So that's really the achievement as an instrument for LIGO is how do you make mirrors so still and then measure such tiny motions. So there's lots of technology that goes into that, but once you've done that technology, then comes the next achievement, which is the actual measurement of gravitational waves and the discoveries. And so LIGO had been going in different phases since about 2000 as an instrument, and then in 2015 we completed a major upgrade to it. And pretty much as soon as the first phase of that upgrade was done, we turned on the instrument, we made our first discovery. So what did we see? We saw the collision of two black holes, and these black holes were over 1 billion light years away. So this is the most amazing, remarkable thing to think about, which is that these two black holes, they collided with each other 1 billion years ago, and those waves were traveling through the universe, and then eventually they hit our instruments, the LIGO and Virgo instruments, and there we were able to record these bumps and wiggles of the space-time itself, and that was the first signals. And what we saw were two black holes that collided. We could tell how far they were, we could tell how heavy they were, we could tell how fast they were going, and that sort of set off a completely new way of doing astronomy, right? We have now seen, waves that come from gravity instead of light.
Precizni satovi mogu u budući da se koriste u razne svrhe. Pošto po Einsteinu vreme zavisi od gravitacije, precizni satovi mogu da se iskoriste da izmere gravitaciju mnogo preciznije nego sa bilo kojim drugim sredstvom. Na primjer, ako tražite rudu ispod zemlje ili naftu ili tako nešto, onda se tu gde nafta ili ruda postoji, gravitacija je promenjena. I ako merite vreme iznad takvog područja, možete da vidite šta je ispod zemlje. Druga primjena koja je vrlo obećavajuća je jedan projekt u Japanu. Japan, kao što znate, ima velike probleme sa zemljotresima gde umre mnogo ljudi. I do sada ne postoji ni jedan način da bi se znalo unapred kad će zemljotres da se desi. Istraživači u Japanu pokušavaju da koriste satove, vrlo precizne satove, da mere najmanje promene gravitacije koje treba da uslede pre nego što se zemljotres desi. Čak kad smo imali samo 30 minuta upozoravanja pre nego što se tako nešto desi, to bi moglo da spasi mnoge živote. Sada idemo da razgovaramo sa Peterom Fisherom, dekanom za fiziku. On je inače fizičar koji istražuje fiziku visokih energija i traži dark matter, tamnu materiju u našem univerzumu. Hajdemo.
Different groups have different cultures and different ways of thinking about their science, and some ways of thinking work better than other ways. The atomic physics group is one that was really started by Wolfgang Ketterle, and he created an environment which is Vladan is one of the leaders of really just an uncompromising commitment to, not just excellence, that's an easy thing to say, but really doing hard experiments. And all the members of that group, which are Wolfgang, Ketterle, Ike Chuang, Martin Zwerlein, and Vladan Vuletic, is they do the hard things. There are other groups that kind of build incrementally, but I think Vladan's leap into quantum computing, which was, to me, very unexpected, that was really very bold. And it looks like it's paying off. It's very exciting. They have a company, which is, I guess, going to sell time on their quantum computer. And I mean, that's just such a great thing. It's great for students. It's great for science. And I think that fits very well with the MIT way of doing things. And I should say Vladan is also a leader in the department, and he plays a big role in choosing who our new faculty are. And he himself is, someone who I think really recognizes quality people and is able to set aside, personal feelings. We all have, personal feelings about a person that might make us wish they were someone different than they were, but if they're a good scientist, that should be more important, and Vladan really acts on that. And so he's one of the real leaders in this department, which I will say is the best department in the world, according to some newspapers. The strategy is really simple here, which is that at every level where we attract people, we really only concern ourselves with how good they are in science and technology. That where they come from, are they rich, has their father given MIT money, what color are they, are really not important considerations. And just really getting the best people together, because really good people appreciate each other. And we have a faculty in the physics department of 75. The average person spends 25 years at MIT. So we have to hire 3 new professors a year. And we'll get applications from maybe 500. And we'll interview maybe 15, 20, and we'll choose 3. We do the same thing with our students. So our physics department graduate program has about 250 students, and we have about 50 show up each year. We get about 1,000 applications, and we have a very long process for choosing. We make offers to maybe 80 people, and then 50 come. And then the undergraduate students are admitted by MIT, so we don't play a role in that, but MIT makes an assessment, and I think as much as possible a meritocracy. Now, are other factors considered? Yes, particularly for undergraduates, because we don't want everybody to be the same. So the admissions, they try to have equal numbers of men and women. They try to have representation across the United States, so not just people from Palo Alto and Cambridge, but people from all over, from in the middle. And people of different races and backgrounds. And then we think it's important that our undergraduate students have experience with students from other countries. So about 10% or maybe a little bit more of our students are international. In our graduate program, we admit the best students, we don't care where they come from. You know, if for some reason the top 80 students were all from Serbia, we would just take all those students.
Hi, my name's Ian Counts. I'm from Los Angeles, California. I went to college at Stanford University, where I graduated with a BS in physics in 2012. And as soon as I graduated, I came here to MIT in Cambridge, Massachusetts, where I've been working on a PhD in atomic physics since 2012. I'm now an 8th year grad student. I will graduate within the next 6 months, probably. This machine that you see is my baby. I spend all my time here. I live in this room. You can hear the noise of the chillers that keep the lasers cool. And I work for a professor whose name is Vladan, who specializes in atomic physics. And what we have here is a machine that traps atoms, and we experiment with the atoms using lasers. I came to MIT. It's a great place that has a very strong atomic physics program. And what got me interested in atomic physics, as opposed to other kinds of nuclear physics or biophysics, was a laboratory class that I took at Stanford, where we got to work hands-on with lasers. And I thought doing hands-on science was so fun, as opposed to just programming and data analysis things on a computer. Here I get to build electronics, I get to build lasers, I get to build vacuum systems. I do so many different things.
Najprecizniji atomski satovi moraju da koriste atome koji stoje u mestu i na koje možemo da merimo dugo vremena, 10-ak sekundi, na primjer, do minuta. Da bismo takve atome uhvatili, nije moguće koristiti atome u atmosferi kao što su sada, jer se oni kreću velikim brzinama. Moramo atome raschladiti na vrlo hladne temperature, tako da ih možemo uhvatiti u zamkama. Zamke su laserski snopovi u kojima hvatamo atome. Postoji samo nekoliko atoma koji mogu i da budu laserski hlađeni i uhvaćeni i koji imaju vrlo precizne prelaze po kojima možemo da merimo vreme. Jedan od tih atoma se zove iterbijum. To je jedan retki metal. Mi hvatamo iterbijum atoma u našoj aparaturi i uspeli smo da ih uhvatimo, rashladimo. Trenutno pokušavamo da izmerimo taj optički prelaz koji bi služio za merenje vremena. U toku od sledećih 6 do 12 meseci nadamo se da ćemo videti taj prelaz, da ćemo moći da počnemo da merimo vreme sa njim i da ćemo isto da stvorimo takozvano uvezana stanja. To su stanja mnogih čestica. Mi merimo vreme ne samo sa jednim atomom, nego sa puno atoma, između 10.000 i milion atoma tipično. I ako koristimo kvantnu mehaniku i stvorimo uvezana stanja, mi možemo da popravimo ili da napravimo još preciznije satove, još bolje satove u budućnosti. I to je što ćemo pokušati da uradimo u sledećih 6 do 12 meseci. Vidjet ćemo kako ćemo da napredujemo.
So as part of my job, I have to spend a lot of time waiting for data to come in. I monitor the data on a computer. And while I'm there, I spend my free time reading articles or even playing the guitar.
Nauka je obeležila moj život. Dovela me u Boston na MIT i otvorila mi vrata sveta bez granica. Vidimo se opet u sledećoj epizodi. Ćao!